Hello, my name is Celeste Barnaby, and in this video, I will be presenting our paper titled PhotoScout Synthesis-Powered Multimodal Image Search. So this is Jen, and Jen is a wedding photographer who shot around 2,000 images at Alice and Bob's wedding last weekend, and is now narrowing those images down to the 200 to 300 that she will deliver to the couple. As is standard practice, Alice and Bob gave Jen a shot list of specific images they want. This shot list includes descriptions like an image of Alice standing with her father, a close-up image of the wedding bands without any people, and an image of Alice next to Bob holding her flowers. These shot descriptions specify logical constraints on the objects present in an image. These search tasks belong to a class of structured image retrieval tasks that require semantic reasoning about the structure of objects in an image. These tasks involve searching a large batch of images and returning all the images that match the user's logical constraints, while not returning any images that do not match them. For example, the task Alice next to Bob holding flowers requires returning this image, which matches all the specified constraints, while not returning this image of Alice by herself, or this image of Alice and Bob together without flowers. Such structured image retrieval tasks are important both for professional photographers like Jen, but also for regular users who increasingly have access to large amounts of visual data. In this paper, we propose a new user interaction model that facilitates structured image search. In general, these structured image retrieval tasks pose two challenges. First, how can a user effectively communicate their intent to an image search tool? For some image search tasks, it's difficult for users to convey their intent using a single modality. In particular, example images alone are often too ambiguous to convey complex search logic. On the other hand, natural language alone also has shortcomings. For instance, natural language queries may contain terms whose meanings are unknown or ambiguous to the search system. To address this challenge, our proposed approach takes both example images and natural language as input. A second challenge is, how can the search tool plan and execute the search logic underlying the user's intent? Existing text or object-based image search tools are powered by vision language models, and despite their object understanding capabilities, they have limited capability in reasoning about complex search logic involving multiple constraints and semantic relationships between different objects. So even if the user is able to perfectly convey their intent, there's no existing technique that can be used to execute complex image retrieval queries. We address these challenges with the following key contributions. First, we present a new multimodal image search interface that combines both natural language queries and example images. This interface is targeted towards structured image retrieval tasks and allows users to communicate their intent interactively. Second, we present a program synthesis technique that leverages the different modalities of input that users can provide through our proposed interface to output a program in a neurosymbolic image query language. And finally, we implement this interface and synthesis system in a new image search tool called PhotoScout. So let's take a look at how PhotoScout works from a user perspective. So suppose my task is to find all the images where the bride, Alice, is standing next to the groom, Bob, and holding flowers. First, I'll write a text query. I'm writing Alice next to Bob holding flowers and selecting the search button. In the search results panel on the right, I see the message, I don't know the terms Alice is holding and Bob. Can you add a few examples and/or tags to show me what you mean? To resolve this, I'll select an image with Alice and Bob, and I'll tag both of their faces. When I scroll over an image, PhotoScout highlights the objects it recognizes in the image. Here, I can see that PhotoScout recognizes Alice and Bob's faces and Alice's bouquet of flowers. Since Alice is holding the flowers, this image is representative of my task, so I'll add it as a positive example. I'll select Search again. Now, in the results panel, I see a subset of the images in my dataset. At the top of the panel, I see a natural language explanation of these search results. It says, I found all images where there is an Alice next to Bob and a person above flowers. This almost matches my task, but it does not specify that Alice must be holding the flowers. And in the search results, I can find an image that does not match my task. Here, Alice and Bob are next to each other, and they are holding the flowers, and there are flowers, but Alice is not holding them. Instead, they are pinned to Bob's jacket. So I'll add this image as a negative example and select Search again. Now in the results panel, I see a new natural language explanation. It says, I found all images where Alice is next to Bob and Alice is above the flowers. This description matches my task, so I'll press the plus button to save my results. Note that Alice holding the flowers is approximated by the spatial relationship of Alice being above the flowers. This approximation works well, but it's not perfect. For instance, here's an image in my search results where there are flowers sitting in front of Alice, but she's not holding them. I can manually remove images from my search results by selecting this minus button next to the image. If I want to, I can also add images to my search results by selecting the plus button next to the image. And when I'm happy with my results, I can submit them. I'll now describe how PhotoScout's synthesis engine works under the hood. Given a specification comprised of a natural language query and a set of positive and negative example images, the synthesizer outputs a program in a neurosymbolic image search query language matching this specification. By neurosymbolic, we mean that this language contains constructs that are interpreted using a neural object detector. A program in this language takes as input a single image and outputs a Boolean value indicating whether the input image should be in the search results. Programs in this language resemble first-order logical formulas with predicates combined using logical connectives and quantifiers. Let's go through these example programs on the right one at a time. This first program returns true if the input image contains a cat. The second program returns true if the input image does not contain any smiling faces. And the third program returns true if the input image contains a person and flowers such that the person is positioned above the flowers. Next, I'll describe the steps our synthesis engine takes to output a set of search results given a batch of images and a multimodal specification. First, the synthesis procedure asks the user to write a text query describing their search task. This query is passed to a large language model, which is prompted to generate a set of programs in our language corresponding to the query, which are then parsed. The LLM is very good but not perfect at outputting programs matching the user's intent, and in particular, it may output programs with terms that aren't in our language. So during parsing, these unknown terms are replaced with holes to produce program sketches. The user is then asked to provide tags for the unknown terms. For instance, if they used a name in their text query, they're asked to tag the face in an image that corresponds to that name. They're also asked to select a few positive and negative example images. Given these program sketches, tags, and example images, the synthesizer grounds the sketches by performing a numerative search over all possible sketch completions to find a program that is consistent with all positive and negative examples and tagged objects. We're then left with a set of complete programs. We heuristically select the best program for this set, apply it to the user's batch, and present the results to the user. To understand how people interact with PhotoScout and gain deeper insight about the strengths and limitations of the proposed approach, we conducted a user study that compared PhotoScout against a baseline image search tool. Our baseline tool, ClipWrapper, is a user interface powered by OpenAI's Clip model. The Clip model is a state-of-the-art neural network for learning visual concepts from natural language supervision. given a natural language description of a search task or a single image exemplifying a search task, ClipWrapper queries the clip model and returns the most similar images. ClipWrapper does not utilize any hard constraints and may return images that do not precisely match a user's query. A central question of the study is, does ClipWrapper suffice for performing structured image retrieval tasks, or is a tool specially designed for such tasks necessary? ClipWrapper's interface closely mirrors PhotoScout's so as to reduce the number of confounding factors in our comparison. So in this user study, we recruited a total of 25 participants. During the study, each participant was asked to complete a training session and then perform 4 image search tasks, 2 using PhotoScout and 2 using ClipWrapper. The participants were given a total of 5 minutes to complete each of the practice tasks and each of the 4 image search tasks. In the course of the study, participants were asked to talk aloud about their search strategies, and we also conducted post-study interviews. So, given a dataset of images, the goal of each task in the user study was to identify a subset of the images matching a certain criteria. Specifically, these tasks involved the following 3 sets of images. Images of city streets, images from a music festival, and images from a wedding. Each task targeted one of these datasets. Here's an example of how a task was presented to the user during the study. Upon receiving this task, users had 5 minutes to collect a set of images that matched this task as closely as possible using either PhotoScout or ClipWrapper. I'll briefly summarize the qualitative findings of our user study. For a more in-depth analysis as well as the quantitative results, please see the paper. We conducted a semi-structured interview about participants' experiences using PhotoScout and ClipWrapper and report the following key findings. PhotoScout's synthesis-based search procedure makes structured image search easier and more efficient. 16 of the 25 participants reported that they thought their results using PhotoScout were more accurate than their results using ClipWrapper. One participant said, "I noticed that PhotoScout is more functional when it comes to relational statements." Second, example images convey information that text alone cannot. 22 out of the 25 participants indicated that example images provided additional information they could not convey in text. One participant said, "I liked that I was able to provide example images because it helped me clarify my intent." Finally, selecting example images is an intuitive process. Every participant utilized example images when completing tasks with PhotoScout, and selecting positive and negative examples was an easy process for most tasks. 11 out of the 25 participants noted that they intentionally selected diverse example images. For example, one participant noted, "For example images, I chose things that could be confusing so as to rule out potential edge cases." Thanks for tuning in, and please feel free to contact me at this email or check out our codebase at this link.